This is Physics 2212 Lab 3 Circuits. The goal of this lab was to create and observe resistor series circuits and RC circuits. And we are also interpreting ammeter readings in terms of current and electric potential. The purpose of this experiment was to predict the behavior of circuits containing resistors in series and parallel, using multimeters to measure the actual values of conventional current and potential differences in the circuit, and we examined the behavior of ohmic resistors and capacitors. Some key physics concepts in this lab is the node rule, which states that the total current entering a junction is equal to the total current exiting the junction, and it follows the principle of conservation of charge. The loop rule states that difference in potential for a round-trip path in a circuit is equal to 0, which follows the principle of the conservation of energy. Electrical resistance is a concept such that the resistance of an electrical resistor can be calculated using Ohm's law, which relates resistance, potential, and current, where V equals Ri. V is the potential, R is the resistance, and I is the current. When resistors are in parallel, the equivalent resistance will follow the rule that 1 over R parallel is equal to the sum of 1 over all of the other resistances. And then when the resistors are in series, the equivalent resistance will follow that the series resistance is equivalent to the sum of all resistances. Another physics concept is the capacitance of a capacitor, which measures how much charge can be stored in a capacitor per unit of potential difference. It is also equivalent to the vacuum permittivity multiplied by the area of one plate of the capacitor divided by the separation distance between the plates. Some key assumptions in this lab was that the wires, the ammeter, and the battery had no resistance on the current and the circuit, and that the wires are a consistent shape and size. Additionally, we assume that current is constant throughout the wire. Here are the initial conditions of the experiment, where the system is the ammeter and the surroundings is the circuit. Here we can see that we had the 2 ammeter, 2 resistor circuit, and we had the RC circuit as well, and we are measuring the current at each point in the circuit. The results of this experiment were that the electric potential did not decrease completely, possibly due to inaccurate measurements and unideal conditions. We see that initially the battery provides a potential difference that is equal to around 3 volts, after which it gets to the 47 ohm resistor. It decreases by linearly until it gets to the next part of the circuit, and then when it reaches the 100 ohm resistor, it decreases more so until it reaches a small amount, but it doesn't reach 0 from what we observed. This is different from what we predicted because in an ideal system, the loop rule states that the sum of all electric potential differences will be equal to 0. Additionally, we use both voltmeters and ammeters to measure the current and the voltage, and the difference is that the voltmeter measures voltage while the ammeter measures current. And here are the pictures of the experiment below. The predicted current in the 2 resistor circuit was around 0.0204 coulombs per second, whereas we observed that the actual current in the 2 resistor circuit was 0.02 coulombs per second. In the RC circuit, the behavior of the capacitor is as follows. When it was charging, the bulb is lit and fades over time, and the bulb is fully dark once the capacitor is fully charged. When the capacitor is discharging, the bulb is lit from the charges accumulated on the capacitor, and it fades over time once the capacitor is fully discharged. The charging time was around 12 seconds, and the discharging time was around 21 seconds. The calculated values and experimental values for current and potential differences were off by a small amount, as we see before. We observed that a more resistant resistor in an RC circuit meant that the capacitor took a longer time to charge and discharge. Swapping the ammeter connections resulted in a negative reading since the current enters the ammeter through the opposite end. Some possible sources of error in this experiment was a lack of precision in the ammeter due to the ammeter resistance, a lack of consideration of the resistance of ammeters or wires, and numerical errors such as rounding or inaccurate measurements, and timing errors when determining charging and discharging times for the RC circuit. What if we charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach fully charged? This ideal model would predict that the capacitor would charge fully almost instantaneously, within 1 second. However, this prediction would not happen in real life because wires have non-zero resistance that increase the time for a capacitor to reach full charge, and we must also consider the innate resistance of a capacitor. When we use an ammeter to measure how long it takes to discharge the capacitor when it was connected directly to the battery, we did not measure time specifically, but we noticed that charging definitely took longer than 1 second. This difference is due to the reasons discussed on the previous slide, including non-zero resistance of wires and the resistance of capacitors.